The system of linear equations has a unique solution. Find the solution using Gaus-Jordan elimination. To use Gaus-Jordan elimination is to turn the augmented matrix into a reduced row echelon form. Not just row echelon form, but reduced row echelon form. So first, we would need to obtain an augmented matrix from this system of equations. The coefficient matrix is 1x, 2y, negative 1z. The second equation, 1x, 0y, 1z. And the third equation, 2x, negative 1y, negative 1z. We use the dot dot or a straight vertical line to separate the left and the right of the equal sign. The corresponding constant on the right hand side are negative 2, 0, negative 3. Usually, we write the entire row 1 first before we move to row 2. We then perform a series of row operations to turn the leading entry 1 in the second row to 0, the leading entry 2 in the third row to 0. Technically, we should perform one row operation in each step, but to save space, we will perform the two operations in one step. To get rid of the 1 in the second row, we will take row 2 multiply negative 1 and add to row 1 to obtain the new row 2. To turn 2 in the third row into 0, we can take negative 2 times row 2 and add to row 3 to obtain the new row 3. Negative 1 times row 2 will be negative 1, 0, negative 1, 0. We take every entry in row 2 and multiply negative 1. We then add to row 1, which is 1, 2, negative 1, negative 2. This will give us 0, 2, negative 2, negative 2, and this will be the new row 2. We obtain an equivalent matrix where we keep the first row 1, 2, negative 1, negative 2, but the second row is now 0, 2, negative 2, negative 2. If we take row 2 multiply negative 2, we will get negative 2 times 1 is negative 2, negative 2 times 0 is 0, negative 2 times 1 is negative 2, and negative 2 times 0 is 0. And we add to row 3, which is 2, negative 1, negative 1, negative 3. We will get 0, negative 1, negative 3, negative 3. We add them column-wise. So the third row in the new matrix is 0, negative 1, negative 3, negative 3. Next, we can turn the non-zero entry 2, which is in the diagonal of the coefficient matrix, to 1 by taking row 2 and divide by 2, or take row 2 multiply 1/2. We will obtain an equivalent matrix. We keep the first row 1, 2, negative 1, negative 2. But the second row is now 0, 1, negative 1, negative 1, where we took row 2 and divided by 2. We keep the third row, which is 0, negative 1, negative 3, negative 3. To turn the negative 1 in the third row to 0, we can take row 2 and add to row 3. This will give us 1, 2, negative 1, negative 2, 0, 1, negative 1, negative 1. And if we take row 2, add row 3, we'll get 0, 0. Negative 1 plus negative 3 is negative 4. Negative 1 plus negative 3 is negative 4. This is not row echelon form yet. We then take row 3 and divide by negative 4. We obtain a new equivalent matrix. We keep the first two rows, 1, 2, negative 1, negative 2, 0, 1, -1, -1. But the third row is now 0, 0, +1, +1. This is only the row echelon form. If we were to use Gauss elimination, we would stop right here. But since we're using Gauss-Jordan elimination, we will need to keep going and find the reduced row echelon form. The reduced row echelon form is the matrix form where the diagonal entries are 1 and all of the entries above and below the diagonal entries must be 0. What that means is that we need to turn the 2 in the first row to 0, the -1 to 0, and so on. To obtain 0 in the second entry in row 1, we can take row 2, multiply -2, and add to row 1. This row operation will give us the new row 1. If we take row 2 and multiply -2, we'll get 0, -2, +2, +2, and add to row 1, which is 1, 2, -1, -2. We will get 1, 0, 1, 0. These will be the entries in the new first row in the new matrix, equivalent matrix. 1, 0, 1, 0. The second row is still 0, 1, -1, -1, and the third row is 0, 0, 1, 1. We then turn the entry in the third column and in the first row to 0, and we can do that by not combining row 1 and row 2, but row 1 and row 3. We can take row 1 minus row 3 to get row 1. 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 1 is 0, and 0 minus 1 is -1. The second row is still 0, 1, -1, -1, and the third row is 0, 0, 1, 1. There's still one more operation we need to do. In the second row, third column, we need to turn this -1 into 0, and we can do that by taking row 2 and then add to row 3 to get row 2 in the equivalent matrix. The new equivalent matrix is now 1, 0, 0, -1. If we take row 2 and add row 3, we will get 0, 1, 0, 0. And then row 3 is still 0, 0, 1, 1. This matrix has 1 in the diagonals and 0 above and below those 1. It is now in reduced row echelon form. What this matrix is telling us is that z equals 1, 1z equals 1, y equals 0, 1y equals 0, x equals -1, 1x equals -1. So the solution of this system of equation is an order triplet: x -1, y is 0, and z equals 1. We still need to double check our work using the given system of equation. We plug in these x, y, and z. The first equation states that x plus 2y minus z. Simplifying this, we obtain -2, and the right-hand side of the given equation is -2, so this checks out. The second equation is x plus z. -1 plus 1 is 0, checks out. The third equation is 2 times x minus y minus z. This is -2 minus 1, which is -3. So the third equation checks out as well. The solution is x equals -1, y equals 0, and z equals 1.